and welcome everybody to MIMO system control. In this lecture we are going ahead. So in last videos you have learned about single input, single output control, and in this video we want to enhance that in a way, make it more difficult, more complicated, but on the other hand more usable in reality. Let us consider an introductional example. You have a tank that's filled with fluid. You have an input stream, an output stream there, and you have an input temperature, output temperature. And what you would like to control is on one hand the level within the tank, and on the other hand the temperature at the output, which is actually, if it's perfectly styled, the temperature within the tank. So how would you do this? One option would be to just use single input control and single output control and use independent loops. One loop for the level, one loop for the level, and another loop to control temperature. Those are possible ways. But what you have to consider is that they might not be completely independent from each other. And therefore, we would like to analyze this example more in detail. And for this, we are just setting up a mass balance, and that's quite easy. You just start with dm divided by dt is input stream minus output stream. And that's, I mean, you know this is directly related to the level. And if you want to control the level, this is completely enough. So level is dependent on level, and that's it. But for temperature, it might be more difficult. To analyze the temperature, we will start with an energy balance within the tank. And that might be eased by enthalpy balance. So dH divided by dt is the same. The enthalpy within the tank is mass times specific heat capacity times reaction temperature divided by dt. And this equals, on one hand, T in times m dot in times Cp, which is assumed as to be constant, minus the output stream, so T out times m dot out times Cp. And plus minus what? Yeah, the heater is still alive, so we have to consider this as well. So plus our heat stream. All right. And now we want to proceed and make this a temperature calculation, a differential equation for calculating the temperature. So we analyze this further. So Cp is to be constant, and then we can write dm divided by dt temperature Cp plus dt divided by dt mass Cp, and this equals everything above. And now we just, so this is all the same, and now we put this on the right side and then divide by m times Cp. And what we will get is a differential equation for the temperature. So it's actually dt over dt, and that should equal T in m dot in Cp minus the output stream, so T out m dot out Cp plus q dot. And now what? Minus the differential equation for mass. So minus dm over dt times tcp. And this all divided by mcp. Okay, so now we have two differential equations that we want to use. And what we can clearly see from this last equation is that temperature is directly related to temperature, but to the mass balance as well. And that's why we cannot control the temperature completely independent or independently from the mass or from the level of the tank. And that's why MIMO control comes in. For this problem, you could find more examples in the literature. For instance, at Lunze 2020, who did Regelungstechnik, also control technology. And there you would choose the second book. It's available from the SLUB. It's from Springer Online, and you can download it directly and check out the necessary chapters. In this example, you find examples in chapter 1.12. Yep, that's it. Okay, now we've analyzed a problem which should be controlled by a multiple input, multiple output control. And this easier example where we assume that we could control them independently, that assumes or accepts that we have an arrow. And this arrow comes here into place. And yeah. Let's write down some characteristics of this of such problems. Okay, there we assume that we can use independent control loops. This is stuff you know, and this is used in industry. Why? Because it's easy to implement. Okay, let's write this down. On one hand, you have independent control loops. And on the other hand, you can use them. I mean, it's not completely wrong to use them. It's completely allowed if they are not coupled strongly. So you can use them when coupling effect is low. So, and that's now a big question, when is the system coupled low enough that you can use independent control loops? In this example, it would be allowed if this mass flow, so the mass change in the tank is low enough. And within this lecture, we will analyze how low it actually has to be, and when you need a multiple input, multiple output control. So in this example, dm over dt needs to be small. Then it's fine. So now it fits. Okay. Why do we want to use it? I mean, now we know that that the control loops are dependent from each other. Why should we use independent control loops anyway? It's cheaper, it's easier to implement. It's easy to implement them. And they are still a standard in the industry. So you will always find them. So it's still a standard, and you quite often ignore this disturbance and accept this as a systematic error within your model. Go more into detail about real multiple input, multiple output control. And as a first step, we want to change the color of the pencil because we see that it is more visible. Yeah, in the last video, we just accepted that we have a disturbance in here that we have accept as a systematic error. But when we use multiple input, multiple output control, we will use we will model this system behavior more clearly. And actually what we have is that the level has direct influence on the temperature, and now we have to model this. Actually, that's it. It could be a tougher job, but let's write down some characteristics of this real multiple input, multiple output control. So what do we know? On one hand, we know that now we assume dependent control systems or dependent control loops. That's one thing that will affect us during the control decisions. And then we have decoupling effects that are modeled. They are modeled. And when do we use such a system? Last time we said, okay, when interaction is low, and this time we say we want to use it when interaction is high. So when we have strong coupling. And again, what strong coupling is that we will learn within this lecture. It's definitely more modeling work. That's a big point. So it's more work during the design process and during analyzing this stuff. And yeah, on the other side, you will have less work in optimization. Yeah, because you've assumed multiple input, multiple output control, and that's more related to the real world. So you are actually shifting work to another point, and it's down to you to decide whether it's worth it or not. Yeah, you will find this very rarely in the industry, so not often used. And we want to add yet. So maybe in the future this will be way more interesting than it's now. Okay, but that's not all. We want to list something more. Something more that describes MIMO control. Another point is that the interaction between the variables influence the control system stability and performance. So, that's one big point that we have to mention. And performance. That's one point. And on the other hand, the feasibility of the control bit depends completely on the overall process. So you are not just analyzing your system or not just analyzing some transfer functions. You always have to consider the whole system as one big thing, and that's what is related to much work. Yep. Point to add. So always consider the whole system and the whole process. And the pairing of measured and manipulated variables via control is a design decision. That is what we did in here. And actually, that's a connection that we draw on the screen, on the paper. And we assume that is true in reality. In this example, that might be true. So the pairing modeled is design decision. Okay. So there are many control systems in reality that actually should have been multiple input, multiple output control systems. So many problems are problems that are directly use cases for multiple input, multiple output control. So these problems. So occur frequent in reality. And on the other hand, you won't find a real usage of this actually modeled control systems in reality. So this is a kind of gap in reality. So, and many control systems, yeah, that's what we said, and multivariable control involves the objective of maintaining several control variables at independent set points. So, on one hand, all right. And in the next video, we will go more into detail for some theory that is necessary for the other part of the lecture. So see you there.